Hi everyone, today a video on polymers, specifically looking at condensation polymerization. So condensation polymerization is a different type of polymerization to one that we've previously looked at in another set of videos called addition polymerization. Our addition polymerization, if you remember, was due to alkenes. Condensation polymerization, though, is a different type of polymerization. And a condensation reaction is when two molecules react together and a small molecule, often water, is eliminated. And so an example would be a reaction between a carboxylic acid and an alcohol. That's our nucleophilic addition elimination mechanism. And we'd end up producing an ester, and we eliminate water as a byproduct. Now, condensation polymers are normally made from two different monomers, each of which have two functional groups. And the key thing is that both of these functional groups can react on either end of each molecule, forming very long chain polymers. And polyesters, polyamides, and polypeptides are all examples of condensation polymers. So examples of these functional groups, or these molecules that have two functional groups, might be a diol and a dicarboxylic acid, as shown at the top. So our diol is an organic molecule that has two OH groups, two alcohol functional groups. Dicarboxylic acid, again, has two carboxylic acid groups at either end, and the R is just representing some carbon chain in the middle. So, as we said, our addition polymerization was from alkenes. We take our monomer, in this case, in the example at the bottom here, ethene, and under high pressure heat with a catalyst, we end up producing our polymer, which would be called polyethene. But remember that addition polymers are essentially long-chain alkanes, very non-polar long-chain alkanes. And typically we make these polymers from one monomer, just in this case ethene. Condensation polymerization is often two monomers, two different monomers, and each of these have two functional groups on them. And so a polyester is made from a diol and a dicarboxylic acid, and a polyamide is made from a diamine and a dicarboxylic acid. And in both cases, when we do these reactions, we get our two monomers coming together. We form a bond. It's either an ester linkage, a COO bond, or a amide linkage, a CONH linkage. They're shown in red. And in both cases, it's condensation polymerization because we lose a molecule of water. So polyesters has the ester linkage, COO, repeated many times. That's a carbonyl, a C double bond O, and then also a carbon single bond to oxygen. And so to make a polyester, we have diols with two hydroxyl groups and dicarboxylic acids with two acid groups. And so the functional groups on each end of the molecule, of each molecule, can react to form a chain. And again, it's a condensation reaction because we eliminate a molecule of water. Now the fibre pteridine is a polyester, and it's produced from benzene 1,4-dicarboxylic acid, otherwise sometimes known as terephthalic acid, and ethane 1,2-diol, sometimes known as ethylene glycol. And so we can see we have our pteridine polymer, sometimes also called PET, that's polyethylene terephthalate. And so we have our diol and our dicarboxylic acid. These react together in a nucleophilic addition elimination mechanism, and we kick out a molecule of water, and we form our PET polymer. And you can see that essentially our polymer chain is composed of these two monomers. I've labelled it A and B, and this would repeat on and on. That's what those sort of dashed bonds are showing, that essentially this unit of A and B repeats again, again, and again. Another way to write this kind of equation is to take our ethylene glycol, to take our terephthalic acid, to write that we have n moles of these reacting, and then we end up producing our long chain polymer, our PET, and we show it just with our brackets around one repeating unit, and then n after the brackets to show that we have n of those repeating units. And if we've made n repeating units, we must have kicked out n molecules of water. Now polyamides are similar. We have an amine and a carboxylic acid, so that's a diamine and a dicarboxylic acid reacting together. Again, it's a condensation reaction because we lose a molecule of water. And polyamides have an amide linkage, sometimes also called a peptide linkage. And this is a carbonyl, a C double bond O, and then that is connected to an NH group. So we have an amide bond essentially. And so to make polyamides, we have a diaminoalkane or a diamine having containing two amine groups and a dicarboxylic acid. And both nylon and Kevlar are examples of polyamides. So nylon 6,6 is made from 1,6-diaminohexane and hexane 1,6-dicarboxylic acid. The reason why it's called nylon 6,6, the 6 is just referred to the length of the carbon chain in between the amide bonds, essentially. So we have 1,6-diaminohexane, a 6-carbon chain diamine, and hexane 1,6-dicarboxylic acid is a dicarboxylic acid that is 6 carbons long. Kevlar is also made from a diamine and a dicarboxylic acids. So we have now benzene 1,4-diamine and benzene 1,4-dicarboxylic acid. And so the examples of these are shown at the bottom. So for making nylon, we have the sort of colloquial name for it. We have adipic acid, and then our hexene diamine. And these come together, a nucleophilic addition elimination mechanism, kick out water, and we form our amide linkage. And there I've shown one repeating unit. To make Kevlar, our 1,4-diaminobenzene, and again this thing called terephthalic acid, react together in a nucleophilic addition elimination mechanism and end up producing, as I've shown here, the one repeating unit of Kevlar with our N outside the bracket. Now Kevlar's strength, you've probably heard of Kevlar being used in bulletproof vests. The strength of it comes from the really rigid chains and these planar aromatic rings. So the fact that we have these planar aromatic rings in the Kevlar, what I've shown in blue and green in the repeating unit there, those are very, very rigid. They don't like to be moved around, and so that's a very rigid chain, as well as the fact that we have these aromatic rings that can start to kind of layer on top of each other and sort of pack together very strongly. We call it pi stacking. Actually, the pi delocalized pi systems interacting between different benzene rings. And so essentially this is really, really strong intermolecular forces that hold it together and give it its strength. Now polypeptides are another type, but essentially they are the same thing as a polyamide. Typically though we talk about polypeptides when we're talking about amino acids coming together. Now polypeptides can be made from a single amino acid monomer or from different amino acid monomers. And the key thing for this is now that our amino acid contains both a carboxylic acid end and an amine end. So essentially, normally we've started from a molecule that is a diamine for a polyamide. We have a diamine and a dicarboxylic acid, two different monomers. For polypeptides, we can make them from just one monomer, one type of monomer, an amino acid, because it has both of these different functional groups on the one molecule. And so the amine group of one amino acid can react with the carboxylic acid group of another amino acid. Again, it's a nucleophilic addition elimination mechanism, and it's a condensation reaction because a molecule of water is eliminated. Now again, because we have this sort of difunctionality, two functional groups on the same molecule, when we've done this reaction between two amino acids, we still have a free amine end, NH2, and we still have our free carboxylic acid end, our COOH. And so this can carry on growing and growing and growing and growing and getting longer into a big polymer chain. And so there's a difference between a polymer like nylon 6,6, where we take two monomers, a diamine and a dicarboxylic acid, which is a polyamide, and a polypeptide, where each amino acid has two different functional groups. So just make sure that you're clear with the difference, that in nylon 6,6, a polyamide, or for a polyester, we have two different monomers which contain different functional groups. So one monomer is a diamine or a dialcohol. The other is a dicarboxylic acid. For our polypeptides, each amino acid is difunctional again, but it has two different functional groups, or not two of the same. So we then get to how do we identify the monomers and the repeating units. So if we're given a very long chain polymer, how can we identify the monomers that it was made out of? So remember that the monomer is the thing that makes the polymer. And so the repeat unit of our condensation polymer is simply found by starting at any point in the polymer chain and stopping when we see the same pattern of atoms beginning again. It's the same way that we worked out our repeating units for addition polymers. We look for where we see the same sets of atoms repeating. Now the key thing was that in addition polymerization, our monomer was normally 2 carbons long because we started from an alkene. For condensation polymers, the monomers can be much longer, can have much longer carbon chains. So we simply have to start at one point and keep going along until we find where those atoms repeat. And so I would say the best way to work out the monomer or the monomers in a condensation polymer is to try and recognize the links formed by the functional groups. So we know that essentially we're going to have either a polyester or a polyamide, and so we're either going to have an ester linkage, a CO double bond and a CO single bond, or we're going to have an amide linkage, CO double bond and a CNH single bond. And so the first thing that I would do is to take our polymer and essentially find where this linkage occurs, find where the ester linkage is or find where the amide linkage is, and to simply break that in half. So we either break at the CO single bond or the CN single bond. Essentially what we're doing is a hydrolysis reaction. We're breaking this polymer open. So break that linkage in the middle, and then because it was a condensation reaction, we've eliminated a molecule of water to make it. We need to add a molecule of water to reform the monomers. That's this hydrolysis part of it, breaking it apart with water. So simply add back the components of water to each ester or amide link. We know, of course, that we must have started with either a diol or a diamine and a dicarboxylic acid. And so if we have this example of our polyester, we find our ester linkage shown in red, the CO double bond and the CO single bond, break it at the CO single bond, and then add back the components of water. So we're going to put a hydrogen from water onto the single bonded oxygen. We're going to put an OH group onto our carbonyl group, and this ends up producing our dicarboxylic acid and our diol. So always look to see where you can see the same pattern of atoms repeating. So in this case, if we start from the left, we've got our green R group, then our ester linkage, then our blue R group. If we then go across again, we then have another green R group. So we've had that whatever the R group might be there, because in this case I'm showing it with colours, that it's green, it's the same as the one we've seen before. That would be where we see our next set of atoms, and so our repeating unit starts and ends before that. So break the linkage and add water back across. Now, addition polymers like polyethylene, polypropylene are not biodegradable because, as we said earlier on, they are essentially long-chain saturated hydrocarbons. They're long-chain alkane molecules. It's the kind of slightly weird naming in that we name them as the monomer, we name them as the alkene, but the actual polymer is a long-chain non-polar hydrocarbon. And so these alkanes are very unreactive because they have strong and non-polar CH and CC bonds. And so there's nothing in the natural environment. They can't be broken down by biological agents. They can't even be broken down by hydrolysis reactions to easily break them down. And so we usually dispose of them in landfill sites along with general rubbish, or we simply burn them, incineration. Now these polyalkenes, these addition polymers, they can be burnt, they can be combusted. This produces carbon dioxide and water. And that's good in one sense because it produces energy. However, if we haven't got complete combustion, then remember that if we have complete combustion, it's carbon dioxide and water. Incomplete combustion might give us carbon monoxide, and that's poisonous, and we don't want that being released into the atmosphere. Of course, also if we burn them, we produce carbon dioxide, which is a greenhouse gas, adding to global warming. And other addition polymers may release toxic products on burning under certain conditions because the polymer may depolymerize and produce toxic vapors. So a problem of this would be if you have a polymer with, for example, a chlorine in it, sometimes on burning you can end up producing HCl gas, which is very toxic. Now the difference is that condensation polymers, such as polyesters and polyamides, can be broken down by hydrolysis, and so therefore they're potentially biodegradable. And so the actual condensation polymerization reaction is to lose a molecule of water. We can go the other way and we can break it apart, as we just saw with trying to work out the monomers, break it apart by adding back a molecule of water, a hydrolysis reaction. And so this means that they're biodegradable, and so they're better for the environment. Now many polyester materials are actually now being recycled, and there are advantages and disadvantages of this. The advantages are that almost all plastics are derived from crude oil, a non-renewable resource, and so if we recycle these plastics, it saves the crude oil, which is expensive and a diminishing resource, as well as the energy used in refining it. If we can just recycle the stuff we have, we can save energy in actually refining the crude oil. If they're not recycled, then they just most likely end up in landfill sites. The problem, though, with the recycling is that the plastics need to be collected, they need to be sorted, and they need to be transported. So we can't just sort of shove all the plastics in one go and recycle them. We have to sort them out into the types of plastics they are, essentially what monomers they've been made from. And we have to collect them, we have to transport them from where we collect them to where we're going to recycle them. This all uses energy, it uses manpower, and it's expensive. And also the melting and reforming of plastics can only be done a limited number of times before the polymer chains tend to break down and shorten, and this degrades the properties of the polymer. So this might be that you have a certain type of plastic that needs to be really kind of really strong. You shouldn't be able to kind of bend it or change the shape of it. And the more and more that you do this melting and reforming process, the properties can change, and so the chains can tend to essentially start to break down and shorten, and this might mean that your chain and your plastic therefore becomes a bit more flexible, which is not what you'd want for that application. So time to have a go at some questions. So we've got some questions here all to do with condensation polymers. So if you want to have a go, pause the video and the answers will be on the next slide. Okay, so the first question was to draw the structure of the monomer used to form polymer P and to name the type of polymerization. So if we look at polymer P, we see that it is a long chain hydrocarbon. There's no other functional groups in there other than just carbon-carbon and carbon-hydrogen bonds. And so therefore this must have been made through addition polymerization. And so the monomer would have been an alkene. And so if you're not happy with finding the monomers from the polymers of addition polymerization, go back to my video on addition polymerization in the alkene series. But essentially we're going to think about these two carbon single bonds on either side, kind of folding back in to make our double bond. And when we do that, we form our alkene. And so in this case, this would be butene, essentially. Question 2, or part B of the question 1, is to find the structures of the two compounds that react together to form polymer Q, to name them, and to state the type of polymerization. So if we look at polymer Q, we see that we have an ester linkage in the middle, a C double bond O and a C single bond O. And so this is a polyester, and so it must have been made through condensation polymerization. And we know that a polyester is a diol and a dicarboxylic acid. So to find the monomers, we find our ester linkage, break it in half, add the constituent parts of water onto either of the species that we now have. So we break our ester linkage apart, we put the hydrogen from water back onto the single bonded oxygen, we put the OH group from water onto the carbonyl part. We do that for both ends, and what we find is that we end up with our diol and our dicarboxylic acid. And then when we go about naming these compounds, start with the diol. So we have a 4-carbon chain. OH groups are on carbons 2 and 3. So this would be known as butane 2,3-diol. And the dicarboxylic acid, we look for our longest carbon chain. That's 4 carbons long. And we have 2 methyl groups as substituents branching off the chain. And so this would be known as 2,2-dimethyl butane 1,4-dicarboxylic acid, or 2,2-dimethyl butane 1,4-dioic acid. It says identify a compound which in aqueous solution will break down polymer Q but not polymer P. So this is the difference here between a condensation polymer and an addition polymer in terms of their reactivity. Remember we said that addition polymers, because they are essentially long chain non-polar alkanes, can't be broken down easily. They're not very reactive at all. However, condensation polymers have these reactive either ester or amide linkages, and hence they are biodegradable because they can be hydrolyzed. And so normally to break this down, we would take a dilute solution of an acid or a base, so we could say HCl, an aqueous solution, or sodium hydroxide, an aqueous solution. Essentially some sort of aqueous solution. Then question 2 was to first of all draw the repeating unit of the polymer formed from the monomer that we were given in the question. And so the monomer again is an alkene, so this is an addition polymerization. And so when we go from the monomer to the polymer, we just break the carbon-carbon double bond, and we essentially make single bonds to each of those carbons. And so this is an addition polymerization, and the repeating unit is shown there with our square brackets, with the single bonds extending out of those, and then N at the end to represent it's a long chain. Naming the type of polymerization is again addition polymerization. Then question B of this was they have the repeating unit of the polyester shown below to deduce the empirical formula of the repeating unit. So remember, the empirical formula is the simplest whole number ratio of atoms. So we can look at our repeating unit and count up the atoms. We have 6 carbons, 8 hydrogens and 4 oxygens. I can divide all of that through by 2, which gives me C3H6O. I can't divide it through by anything else. Anything else would give us a non-whole number. And so remember that the empirical formula has to be a whole number ratio. And so our empirical formula is C3H6O. We then have to draw the structure of the acid, which could be used to prepare this polyester and give the name of the acid. So if we look at our repeating unit, essentially what we're going to do is find our ester linkages, break the ester linkages to get our monomer back, and add back the OH from water onto the carbonyl to give us our diacid. And so we can see that our acid is 4 carbons long. And so when we name this, it would be butane 1,4-dioic acid or butane 1,4-dicarboxylic acid. And then finally, to give a reason why the polyester is biodegradable, and the reason is because it contains a reactive ester linkage. This is because our ester linkage is a polar group. We have our polar CO double bond, we have a CO single bond, and hence we have lots of dipoles, and we have a very delta positive, very electron deficient carbon atom, and hence it can be attacked by water, acting as a nucleophile. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please consider leaving a review on the tuition website. I offer online tuition for chemistry, so please check out my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, you can always feel free to email me. I'll be happy to help.